Welcome to my channel. Today we'll take a look at how to calculate the eigenvalues and eigenfunctions from an ODE. Okay, so the question goes something like this. Compute the eigenvalues and eigenfunctions of let's take our ODE y double prime plus lambda y is equals to 0 and our domain ranges from 0 to L. Now we can solve this same problem for different boundary conditions, but let's look at a simple Dirichlet boundary condition. With boundary conditions given by, so this is our Dirichlet boundary conditions. Okay, now let's take a look at the solution. Now we have this ODE. This is a second order ODE, so we know how to solve a second order homogeneous ordinary differential equations. So the characteristic equation of the ODE is r squared plus lambda is equals to 0, right? The solution to the characteristic equation is the two solutions will be plus or minus square root of negative lambda. Now we have three different cases to consider because the form of the solution will be different for three different values of lambda. Now we have to consider three different cases is the form of the solution will be different for lambda is equals to 0, lambda is greater than 0, and lambda is less than 0. So if lambda is 0, then we'll get a trivial solution. If lambda is less than 0, now if lambda is less than 0, this is a real number, this will get two real numbers and we'll have a different solution. And if lambda is greater than 0, then we'll get an imaginary number in here, so we'll have three different solutions, right? Now let's look at three different cases. Case 1, when lambda is equals to 0, the solution will be y of x is equals to a plus b of x. Now if you do not know how to write this solution at this point, then I recommend going back and watching the videos on how to find the solution to a homogeneous second order ODE. When lambda is less than 0, the solution will be so a e to the power of negative lambda x plus b e to the power of square root of negative lambda x, right? Now case 3, when lambda is greater than 0, the solutions will be a cosine of square root of lambda x plus b sine square root of lambda x. I just realized this x is outside of the lambda is so right, so x is outside of this square root. Now let's look at the cases. Now when lambda is equals to 0, now we have our Dirichlet boundary conditions. This is our solution, a plus b of x, and our boundary conditions is y sub 0 is equals to 0, which implies a plus b times 0 is equals to 0. That just implies a is equals to 0. And our second boundary condition, y sub l is equals to 0. Now a is already 0, then b times l is equals to 0, and that just implies b is equals to 0. Thus we get a trivial solution. So no eigenvalues and no eigenfunctions when lambda is equals to 0. So now let's look at the other cases of when lambda is less than 0, right? When lambda is less than 0, we have the real roots for this. When lambda is less than 0, we have the real roots. Our solution is this. This is our solution, a e to the power of square root of negative lambda x plus b times e to the power of negative square root of negative lambda x. So let's apply our boundary conditions. This is our solution. B e to the power of negative lambda x. Now our first boundary condition, y sub 0 is equals to 0. Then we just get a, now 0 plus b e to the, now this is just, this part just goes to 1, this part also goes to 1, so we get a plus b is equals to 0. And let's look at y sub y of l is equals to 0. Then we get a e to the power of l plus b e to the power of is equals to 0. Now from here a plus b is equals to 0, then b is also equals to minus a, right? So we can just use a e to the power of negative lambda l minus a e to the power of l is equals to 0. And this is only possible when a is equals to 0. So from here we get a is equals to 0 and b is also equals to 0. Thus trivial solutions. And we do not have any eigenvalues for when lambda is also less than 0. Now let's look at the third case when lambda is greater than 0. When lambda is greater than 0, our solution was, this was our solution, right? This is the solution to our ODE when lambda is greater than 0. A cosine of square root of lambda x plus b sine square root of lambda x. Now y sub 0 is equals to 0. Then we get a cosine. Now if you put 0 in 0, you cosine negative lambda times 0 plus b sine. Now this is just 0. Now sine of 0 is 0, so this entire thing goes to 0. Similarly, from here we get a is equals to 0. Right? Because cosine of 0 is 1, so a is equals to 0. Now let's apply the second boundary condition, y of L is equals to 0. Now a is equals to 0, meaning this, we do not have this part, right? So b sine square root of lambda L is equals to 0. Now in this case, b does not have to be 0. In this case, b does not have to be 0. This equation is satisfied when sine this is 0, then this equation is satisfied. Now when can sine be 0? Sine can be 0 when our this square root of lambda L is just plus or minus n pi, and when n is plus or minus 0, plus or minus 1, plus or minus 2, and dot dot dot. For this scenario, b does not have to be 0. So what's our conclusion? The conclusion is, thus the value of lambda, the equation does not have the trivial solutions are what are the cases when what are the possible values of lambda for which the equation does not have a trivial solution. So the possible values of lambda for which the equation does not have a trivial solution are lambda is equals to plus or minus n pi divided by L whole squared, right? Which just happens to be n pi n pi by L squared, or we can just write it as n squared pi squared divided by L. Now if lambda is equals to 0, so if n is equals to, what are the possible values of n? Now the possible values of n are plus or minus 1, plus or minus 2, plus or minus 3, dot 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 dot. But we can just say plus or minus 0. Now if n is 0, then we get a lambda to be 0, which again happens to be case 1, right? And since we have n squared, we do not have to use plus or minus 1, plus or minus 2, plus or minus 3, because it's n squared, so you are getting the same answer for both of the values. So n can be 1, 2, 3, 4, dot 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 dot. So the eigenvalues are lambda is equals to lambda n equals to n squared pi squared divided by L. N is 1, 2, 3, dot dot dot. Now what about the eigenfunctions? Thus the corresponding eigenfunctions are eigenfunctions associated with the eigenvalues are, again we go back up here, this is a solution. Now we calculated a to be 0 and b sine square root of lambda x, that's our solution. So we usually denote the eigenfunctions with function u of x is equals to use a sine n square pi square L square divided by x, n is 1, 2, 3, and then a is the constant that was b in the solution, right? And this is the value. So this is how you calculate the eigenvalues and eigenfunctions from a given ODE for a given boundary condition. So we can mark this as a solution. This is our eigenfunction. This is our eigenvalues. Hope you liked my video. Thank you very much.